I'll get to an application of this formula in just a moment, but there is a slightly different way we can think about the volumes of these shells. If you prefer, you can take it or leave it. So again, keeping this idea about building cylindrical shells using some section of the x-axis, I'll call this delta x. I'm using some x coordinate, and I'm using the value of the function to define my height. We get this cylindrical shell. Well, you can also think about the volume of this shell as, well, what if we just sliced this cylinder in one spot? You know, just take a pair of scissors, snip it right there, and unroll it. Well, I should expect that to unroll to just be this rectangular prism. It's not exactly right. But if the original cylinder had a circumference of 2 pi x, I'm expecting my unrolled version to be 2 pi x units wide. Well, the height is going to stay the height, and the thickness is going to stay the thickness. So it still looks as though my volume is 2 pi x times f of x times delta x. Now, I can identify all three of these quantities in my volume formula, in my integral formula. So I'm integrating from a to b, and in my integrand here, I see all three quantities. Volume is the product of three different length measures. Here I see circumference times height times thickness. That gets me some piece of volume. And the integral is the tool which adds them all back together to find the total volume of whatever horrible Jell-O mold I'm looking at. Let's actually calculate volumes of horrible looking Jell-O molds. So our function is going to be y equals 2x squared minus x cubed. And we're going to use that to define some region on the xy plane between this function and y equals 0. Here is that picture again. Now, for coordinate x, I'm going to build this cylinder. The cylinder has height equal to 2x squared minus x cubed. The width of my cylinder, as always, is delta x, and the radius of my cylinder, I need the radius to get my circumference, is going to be x. I'm rotating around the y-axis. So how far am I from the y-axis? I am x units away from the y-axis. So x is my radius. Okay. So if x is the radius, the circumference is 2 times pi times x. The height, as I already said, is 2x squared minus x cubed. So my integral looks like this. Volume is equal to the integral from 0 to 2 of 2 pi x times 2x squared minus x cubed times dx. And I see here circumference, height, width. Now, where did I get those bounds? Where did I get that 0 to 2? Well, my graph of the function crosses the x-axis at 0. You know, plug in an x equals 0, I definitely get 0 there. And at 2. 2 times 4 minus 8 is 0. So those will be my two different bounds for my integration. And after I've written out the formula, the integral that I have left is just a polynomial. How nice. I can pull out that constant as I usually do. Let's pull that 2 times pi out. My antiderivative now will be x to the power of 4 divided by 2 minus x to the power 5 divided by 5. I don't like that so much. I think there's a typo here that this should have been a quarter of x to the power 4. So naughty on whoever typed these up, but I know you caught that as soon as I switched slides. This formula allows us to calculate that volume with just a simple antiderivative of a polynomial, and it's the geometry that told me what is the correct polynomial to integrate.